Sure. Okay, so today's talk is by Yuxi Han. She's working in Purdue University, and she's gonna talk about quantitative homogenization of first-order convex Hamilton-Jacobi equations in the Wasserstein Stein space. Okay, please, Yuxi.
Thank you for the introduction. First, I would like to thank Han and Hilo for organizing this online seminar. And also, I want to thank everyone for attending my talk today. So in my talk today, I will talk about my recent work on the rate of convergence for homogenization of first-order Hamilton-Jacobi equation in the Wasserstein space. So this is a joint work with Jian Ding, Ibrahim Akron, and Antonio Stichizes. So they are people from Michigan. Okay. So this is the outline of my talk today. So I will begin by introducing the framework of mean field control as a motivation. And we will see how Hamilton-Jacobi equations naturally arise. And then I will review the literature on quantitative homogenization results in finite dimensional space first. And then I will introduce some related homogenization results in infinite dimensional space. And then I will present our main results. In particular, we will see the rough proof idea for a simpler case where the Hamiltonian only depends on the fast variable and the momentum. Okay. So let's begin by a real world example. So suppose a crowd is trying to evacuate from a large room, for example, a museum. And then the goal is to try to go away or exit the room as quickly as possible with a prescribed time. Okay. And then there are several exits located in different parts of the room, as we can see in the picture. So there are three. Okay, and then because we want to do this as quickly as possible, so there are many factors that will affect people's decisions. So, for example, if some place gets really crowded, we might want to avoid going closer to that area. Okay, or maybe some routes would contain going upstairs and then go downstairs. We don't want that either, so it takes more time and energy. And maybe there are some repeated small obstacles like stairs or exhibition areas. We also want to take that into account. Okay, so there are many factors affecting people's decision. And the mathematically, the way we want to model this problem is to use the mean field control framework. So in particular, we consider filtered probability space, which is atomless and rich enough. So typically one that supports the Brownian motion. Okay. And then we denote the starting time to be little t, and then the ending time is big T. So we are given by an initial distribution, little m. Okay. So here the notation P sub n, P sub 2 of RD, this is the space of Wasserstein space of probability measures on RD with finite second moments. Okay, and then the metric here is Wasserstein 2 distance. And then for a representative agent, we consider the following dynamics. So this dynamics is actually relatively easy. So we require the law of x at the beginning time little t is equal to the given measure m. So here the notation script L means the law of some random variable. And then we require the velocity of my process to be alpha s. And this alpha is admissible control. So here, the admissible controls we are considering are all f progressively measurable, and they have finite expected L2 norm in time. Okay. All right, and then the cost functional here is given by two parts. So the first one is given by some Lagrangian L as the running cost. So here L depends on four slots. So the first slot here is in d-dimensional torus. So we have a microscale parameter epsilon, and this denotes the small scale heterogeneity we saw earlier in the evacuation example. And then the second slot is the large scale variable, which lives in RD. And then the third slot is the velocity or the control slot, which also lives in RD. And then the fourth argument here lives in our Wasserstein 2 space here, where it depends on the law of my process access at the moment. So this is actually reflecting the fact that the cost actually depends on the current population density, just like in the evacuation example. Okay, so besides this running cost, we also have a terminal cost given by some function g. So this g takes in values in P2, and we evaluate the cost at the big T. So here I have g of the law of x big T, where we is the ending time. Okay, and then we are trying to take the infimum over all possible controls, which are progressively measurable, and the corresponding dynamics xs. Okay, so we are trying to minimize over all possible controls and the path x, and we denote the resulting value by big U epsilon. So this depends on t, little t, which is our starting time, and the given initial measure m. Okay. So the dynamical programming principle for this value function is actually proved by Jata, Postman, and Tan in 2022. Okay, so in particular, they proved the dynamical programming principle for this value function, and they also proved this value function solves the following first order Hamilton-Jacobi equation in the Wasserstein space. So first, notice this equation is not an initial condition equation, so it has a terminal condition where the terminal condition is given by this g in our terminal cost inside the value function. And then, so let's look at the first equation here. So we still see the microscale variable in the first slot. So H is the Lagrange transform of the Lagrangian in the cost value function here. And then here is the third slot. So this slot, I have this notation D sub M U epsilon. So this is actually the Wasserstein derivative of big U epsilon. I'm not going to give the rigorous definition for this derivative because we are not going to use this. And notice there is an actual dependence for D sub M U epsilon in RD. Okay. Okay. So this is our equation.
Can I ask a quick question?
Yes.
So you just told us script L describes some SDE, but typically, can you explain just quickly what is the typical SDE? Script L?
Yes, so script L means the law of this random variable.
Yeah. But
yeah, so for a typical SC here, so there's no grounding
sorry,
motion.
I misunderstood. Okay. Sorry. No, that's fine. Okay. Please go ahead.
You're good. Yeah.
Yes.
So this is the dynamics. So there is no grounding motion. It's just the velocity, and then we also require the initial law to be m.
Yes. Yeah. Sorry, I totally misunderstood. Okay. Fine.
No, you're good. Yeah. Thank you for the question.
Yeah. Can I say one thing here for the students?
Sure.
So for UC problem, what is interesting in the cost functional is that if there's no law script L of XS, and it's a normal optimal control problem, right? First order. But here there's a law coming in, meaning that each player is playing, but see sort of the total density of the populations as something happening there. So that's why it's called mean field control. Yeah. Thank you.
Yeah, and also here we can think of there's a central planner trying to minimize this cost because the terminal cost only depends on the density of the population. Yeah, so if the terminal cost also depends on, say, particular dynamics X, then it's a mean field gain, not mean field control.
Right. And if you have the Brownian motion in the SD, like what Hiro said, then it's a more difficult problem, right?
Yes. Yeah, that's actually what we are working on right now.
Yeah. Thank you.
Okay, so let's continue with our equation here. So when I say big U epsilon solves this equation, I have to give you the definition of, say, a viscosity solution to this first order Hamilton-Jacobi equation. There are different ways to define solutions to this equation. So what we mean here is actually in the lifted sense due to Lyons. So in particular, we consider a Hilbert space, H, denoted by H here, which is all the L2 random variables, basically. And then the inner product is given by the expectation of the product. So for any function, phi, originally defined on P2 of Rd, we can define its lift by phi hat. Okay, so now phi hat is defined on this Hilbert space. And the definition is actually very easy. So we let phi hat of x to be phi of the law of x. So we just plug in the law into the original function. So now this function lives in the Hilbert space. And then how can we lift the whole equation to the Hilbert space? So to get a motivation for that, so let's suppose everything is nice. So the solution is U epsilon is smooth enough, right? So we can still consider its lift, which is denoted by U epsilon hat of x. So it's given by U epsilon of the law of x. And then in fact, so the Wasserstein derivative is actually equal to the gradient of U epsilon hat in the Hilbert space. So here, for the Wasserstein derivative, I have to plug in the law of x in the second slot. So the third slot with x, and this is equal to basically the Fauché derivative inside the Hilbert space. Okay. And then further, we can verify that U hat solves the following first order equation. So here the Hamiltonian H epsilon hat is defined to be the expectation of the original Hamiltonian H with x and the law of x plugging in. Okay. So here the first law I have x over epsilon, and then second I have x, and then I have law of x. So P here is still the momentum slot. And then for the terminal condition, I have G hat, which is also the lift of big G. Okay. So now we have an equation defined on the Hilbert space, and there is a way to give the definition of viscosity solution to this equation. Okay, so here is the definition. So for this lifted equation, an upper semi-continuous function V defined on the Hilbert space is called a viscosity subsolution if it satisfies the usual viscosity subsolution conditions. For example, at the terminal time big T, right? So we have V is less than or equal to G hat. And then for any smooth function phi that is touching V from above, say, at some point T0, X0, then I have the equation with phi plugging in evaluated at T0, X0 is less than or equal to 0. And the definition for super solution is similar. Okay, so this is just a usual definition for viscosity solutions on Hilbert space. And then further, we can look back at the original equation and define its solution as following. So we say a function big U epsilon is a viscosity solution of the original equation if its lift is a viscosity solution of the lifted equation. Okay. So here we just use the lifted equation in the Hilbert space to define the solution. Okay, so for this definition, we do have comparison principle. This is due to Gambo, Mayaga, and Swench in 2021. So we do have a unique solution for this first order Hamilton-Jacobi equation. Okay, just like any other homogenization problem, because of the small scale epsilon, usually it's costly to handle the original equation HJE sub epsilon. And intuitively, we will want to let epsilon go to 0 and hope to find something simpler in the limit where it's less costly to handle. And indeed, that's the case for us. So as epsilon go to 0, we expect that in the limit, u epsilon actually converge to some limit u, and u solves the corresponding limiting equation with a simpler Hamiltonian. Here I use the notation h bar. So h bar is actually the effective Hamiltonian. So in this case, it's a little bit complicated because it has many dependence here. But say with x, p, and fixed, this is just a unique constant that solves the corresponding cell problem, still on the d-dimensional torus here. So I'm not going to give the more detailed formula for h bar here, just to save some time. Okay, so in a second, we will establish the uniform convergence of u epsilon to some limit u and the rate of convergence together. Okay, so before we do that, let's quickly review the literature in the finite dimensional case. So in the finite dimensional case, for general non-convex Hamiltonian with multi-scales, it was first done by Capuzzo, Di Chata, and Ishii in 2001. So they proved the rate is O epsilon to 1/3. So there the equation is defined on Rn, and they also consider multi-scale, both x and x over epsilon dependence here for the Hamiltonian. So the rate is O epsilon 1/3. And then for H is convex in P, there are many works. So first, for the case where H does not depend on the large scale variable, it was first done by Mitake Chen in 2018, where they proved the lower bound is O epsilon and it's optimal. So for the upper bound, they need some additional conditions. So here the rate is uniform in both spatial variable and time. And later, again by Chen Yu in 2021, they proved the optimal rate of convergence for this case is indeed O epsilon. So the main proof idea there is to use optimal control formula for U epsilon and U and topological lemma on decompositions of curves by Brago in 1992. So that closes the whole discussion for the Hamiltonian that's convex in P and does not depend on the fast variable. And then for the large scale variable. And then for the multi-scale case where H can depend on X, so there was first done by Tu in 2020. So he showed in 1D the optimal rate is O epsilon, and he needs some additional assumptions on H. And later in 2023, John and I showed that the rate is actually depends on time. So here for time is large, say greater than or equal to square root of epsilon, the rate is square root of epsilon here. And then for t is relatively small, smaller than square root of epsilon, we have something slightly better, which is the minimum of t and epsilon. So better rate, at least O epsilon. Okay. So in the multi-scale case, the convergence rate actually depends on time. Okay, so that's a quick review for the literature on finite dimension. And now let's look at infinite dimensional results. So for infinite dimensional results, it was first done by Gambo and Dorasco in 2021. So they studied the qualitative homogenization of first order Hamilton-Jacobi equation in infinite dimensions. So they studied the gamma convergence of the integral functional. And then very recently, Park studied the quantitative homogenization of first order Hamilton-Jacobi equations directly posted in Hilbert space L2 of the torus. And then he showed for non-convex Hamiltonians general case, the rate is O epsilon to the 1/3. with some additional assumptions on the initial conditions. And then my collaborator, Zichardis, also did some homogenization problems for second order Hamilton-Jacobi equations in the Wasserstein space. In particular, he studied the coupled systems of controlled slow and fast Makin Velasco SDs, so more complicated dynamics than what we are doing right now. Okay, so that's the literature for infinite dimensional case. Now let's go to our results. So first, I want to introduce our assumptions here. So the first assumption is for the Hamiltonian. So here we still assume our Hamiltonian is convex in the momentum slot. And then further, we assume the growth of our Hamiltonian is basically quadratic in the momentum variable and uniform in any other variables here. So the notation C sub 1H K0 and C sub 2H here, they are all constants. And then further, we assume an actual regularity for the Hamiltonian age. So in particular, it's basically locally Lipschitz. So when the momentum slot is bounded, it's Lipschitz in every slot. So here, when I say Lipschitz, for the measure slot, we are considering the Wasserstein 2 distance metric here, which I use the notation D sub 2 to represent here. So the constant, so C sub H is still a constant here. Okay, so these are the three assumptions on the Hamiltonian. And then for the initial condition G, the terminal condition G, we assume it's bounded and also Lipschitz with respect to the Wasserstein 2 distance. Okay, so these are the assumptions. And then this is our first result. So let's consider the easiest case where H does not depend on X or the measure. So in this case, we prove that the rate of convergence is O epsilon, and it's uniform in both time and the measure. Okay. So to the best knowledge, to the best of our knowledge, this is the first result about quantitative homogenization for Hamilton-Jacobi equation in the Wasserstein space. And also the rate here is optimal. So to see the rate is optimal here, we have to consider the equation in finite dimension. Okay, so let's look at the finite dimensional equation here. So here, little g is assumed to be bounded and Lipschitz. This is our terminal condition here. And then let's say little u epsilon is a unique viscosity solution to this first order Hamilton-Jacobi equation posted on RD. Okay. And then, so supposing our infinite dimensional equation, we consider a special initial condition, terminal condition G, which is defined by the integral of this little g against any given measure M. Okay, so for this particular terminal function, we can show that the solution is actually given by the following formula. So big U epsilon of t comma m is actually equal to the integration of little u epsilon against this given measure M. Okay, so to see this, it's actually not hard. So we just take this finite dimensional equation. So we integrate the whole equation, say, with respect to some given measure M. Okay, I just did an integration in the first equation here with respect to M. And then for the first term here, so the derivative with respect to t, when I integrate, this is exactly the derivative of big U epsilon. And then for the second term here, we have the gradient of little u epsilon. Okay. And if our big U is given by the integration of little u epsilon, so there is a relation between the gradient of little u epsilon and the Wasserstein derivative of u epsilon. So we can actually compute. So here I'm not going into detail, but when I take the Wasserstein derivative of big U epsilon, when it's defined like this, it's when you compute, this is exactly the gradient of little u epsilon. So in other words, for this slot here, the second slot in the Hamiltonian, I can replace this by big U the Wasserstein derivative of big U epsilon, and we can see big U epsilon given by this formula indeed solves this equation in the infinite dimensional case. So here also the terminal condition becomes big G when I integrate both sides. Okay, so then this shows indeed this is the solution. Okay, so I'm going to erase this. All right. And then for the particular measure, delta measure at any point little x, big U epsilon of t delta of x is indeed our little u epsilon of t comma x. So the theorem above here we proved actually implies the rate of convergence for this little u epsilon is O epsilon, okay, which recovers the previous results in finite dimensional case. So in the finite dimensional case, Chen, we showed this is optimal. So indeed for us, the rate is also optimal here. Okay, so let's talk about the proof idea here. So usually for the homogenization results, people would first start with quantitative result, right? So we will try to prove some nice regularity properties of U epsilon. Usually we prove it's uniformly equicontinuous. And then by Azela-Ascoli, we can get locally uniform convergence to some limit U, say. And then we try to characterize the limit. So when we try to characterize the limit, usually we would construct some auxiliary function, right? And then try to argue for this auxiliary function, we do have a local max. And then we use the definition for viscosity solution of U epsilon, and then try to pass the limit and argue the limit also solves the corresponding Hamilton-Jacobi equation. But in our case, it's actually not feasible here because the space is not good. So the topology on the probability space P2 of RD is not locally compact. So we cannot really argue like what we did in finite dimensional case. So indeed, in this case, what we do is we will establish the quantitative result first. In particular, we will use the optimal control formulas for U epsilon, and then we prove U epsilon converges to some limit U bar with the rate of convergence O epsilon directly. So this convergence is uniform, which will help us to identify U bar directly after this. So we can identify U bar with U. So there's no proof for the qualitative result first. So we will establish them all together because qualitative result gives us uniform convergence, while if we start with quantitative result, it's only locally uniform convergence, which is not enough in our infinite dimensional case. Okay, so in particular, there are two important ingredients in our proof here. So first, we will consider a bunch of equivalent formulations of our value function U epsilon. So you will see in a second, the original optimal control formula for U epsilon is relatively hard to handle. So we have to derive other equivalent ones that are easier to handle. And in the process of that, we will also have some velocity bounds. And there is a very useful and important randomization technique to help us with the to prove the equivalent formulations. You will see in a second. So that's the first part of our proof. And then the second ingredient is the cost function M from Chen Yu. So this cost function has very nice properties like super and sub additivity, which will give us a nice quantitative result for homogenization. Okay, so let's look at the proof now. So like I mentioned, I will look at the optimal control formula of U epsilon. So here I just copied down the optimal control formula for U epsilon earlier in the slides. So in particular, the control sets here are all the control set is progressively measurable with respect to my filtration here. So this progressive measurable controls are very hard to handle because progressive measurable is very abstract, right? So we have an abstract filtration. And when I say progressively measurable with respect to that, I don't know what kind of information it has. So instead of looking at these controls, maybe we can think of some simpler controls and then try to compare them. So the simpler controls I can think of is the following. Okay, so here I use A sub 1 to denote this new set of controls where all the controls are measurable with respect to the largest sigma algebra. So I require alpha is measurable with respect to the broad sigma algebra in terms of the time, cross this F is actually the largest sigma algebra in my probability space. Okay. So it contains all the information. All right, so apparently when I compare these two definitions, I can see, right, so A1 contains more controls than A, right? So the value function, the corresponding value function for the A1, I denote here by U1 epsilon. So this is actually less than or equal to U epsilon, just because it's taking inf over a larger set. Okay. So we only have an inequality here. Can we do more, right? So can we compare this to more carefully? Maybe we can have them to be equal. Okay, so indeed in this case, they are equal, even though on the surface, it's very hard to see they are equal to each other. Okay, so let's see why they are equal to each other. So to prove they are equal or equivalent, I have to introduce a third set of controls. So the things are getting more complicated. Okay, so for the third set of controls, I introduce a Gaussian variable Xi here. Okay, this Xi is independent of anything, so it's independent of the random, the Brownian motion or anything, and it lives in the very beginning. So the sigma algebra of Xi is inside the sigma algebra at time is equal to 0. And then my second set of controls here, I require them to be measurable with respect to this Gaussian random variable. Okay, so when I say measurable, basically I can write my control in the form of alpha tilde here of Xi. So alpha tilde is actually defined on RD. So the randomness is only coming from Xi here. So I still need the L2, expected L2 norm to be bounding here. And also I call the corresponding value function for this admissible set of controls to be U2 epsilon. All right. So I have this weird third set of controls. So right now, let us do a summary here. So I have 3 types of controls. The first one is the original one, progressively measurable with respect to the filtration. And then the A1 here is the largest possible set of controls we can think of. And here A2 is a special type where it's measurable with respect to some Gaussian random variable. So when we look at this definition, we can see the relation between these 3 sets. We already compared A and A1. So this A2 is measurable with respect to Xi, where Xi lives in time 0. So it's definitely progressively measurable because the information of Xi will always inside the sigma algebra when T becomes larger. So here A2 is the smallest one, so it's contained in A, and the largest one is A1. Okay. Because of the relation here, we have the inequality for the value functions. So U1 epsilon is the smallest one, U2 epsilon is the largest one, U epsilon is in between. Okay. So we, instead of proving U epsilon and U1 epsilon are equal, instead we try to handle U1 epsilon and U2 epsilon. Okay, because U epsilon is hard to handle. And the goal here is try to show U1 epsilon is greater than or equal to U2 epsilon. And then the 3 are all equivalent. Okay, so let's try to prove this. So remember, our goal is to show U1 epsilon is greater than or equal to U2 epsilon. So U epsilon is not in the picture here. So for U1 epsilon, this is my optimal control formula. I can do a change of variable. All right. So I call the law of the terminal random variable to be nu. So nu is the law of x big T. And then I call the random variable at the beginning to be x and the ending time to be y. And also I use the notation gamma to denote the path. So for each omega, I can define gamma of s omega to be the big X s omega. And then here dot means the derivative with respect to time s. So this is exactly the control alpha s. So this is just a change of variable or names. And then I can rewrite the whole optimal control formula here. So this looks complicated, but it's actually not too bad. So there are 3 inf. Okay. So the very outside inf here is over all possible terminal measure in P2 nu here. Okay. When I fix the terminal measure, I consider all the couplings. So in particular, I consider all the L2 random variables, X and Y, the pairs where the law of X is M, which is the given initial measure, and the law of Y is the measure at the terminal time. Okay. And then when I have a such pair, I consider all the paths that maps from X to Y. So this is actually related to optimal transport and transport planning here. So the gamma of X comma Y. So gamma is a path. Okay, it has an actual dependence on omega. So when omega is fixed, this is just the usual absolute continuous curve that takes value of that goes from little t to big T. And then when I fix the time at little t, gamma of little t is big X. When I fix the t at the terminal time big T, this is the random variable Y. So indeed, this admissible set for gamma is all the paths that connecting from X to Y when I fix a coupling. And then inside, I'm just taking the expected value of the running cost and the terminal cost. This is just a change of variable. Okay, I just copy it here. And now there is an important velocity bound in expectation. So the expected difference between x and y squared is bounded by some constant m0 times the time difference squared. Okay, so this is this is just a velocity bound. This m0 does not depend on anything here. And now, how can we deal with this optimal control formula? So now what I'm going to do is I'm going to change the order of this inf and this expectation here. So in particular, I'm going to consider a cost function h sub epsilon. So this is just the m cost function in the previous finite dimensional case. So this function has 4 slots. So there are 2 slots for time, 2 slots for location. So here I have T1, T2, X, Y. So this is the minimum cost for us to take the time from T1 to T2 to go from X to Y. So here the infimum is over all absolute continuous curves gamma, where it starts from X and ends at Y. And then the cost here is given by the Lagrangian, the integral of the Lagrangian here. So you can see here all the paths inside this inf, they are deterministic. There's no omega. Okay. And then I take the expectation when I plug in my coupling X and Y into the 3rd and 4th slot here. Okay. And then I throw in the terminal cost G and then take the inf over all terminal measure. So here the expectation is outside this H function. So before I take the inf over the path outside, and then inside I take the expectation. So before the path is more restricted, right? So I have to require this path is measurable with respect to the largest sigma algebra. So there's an actual measurable condition for that path. But here in this second line here, I don't have any measurable condition for my path. So here I have inequality. So indeed, when I consider this, I have more paths. So I have less. So the original one is greater than or equal to this cost here. Okay. So I just copy what we get so far up here. All right, and then next, there is a very important measurable selection theorem, which I'm not going to prove here. So you can see the next step is I'm trying to construct some control that will be admissible for U2 epsilon, starting from this H epsilon. So H epsilon, if you go back here, okay, so this is the inf, right? So for any small delta, by definition, indeed, we can find some admissible path gamma so that it's delta optimal, okay? But the thing here is we have to do it smartly, which is I have to make sure when I vary the starting and ending point x and y, the path I get for each pair of starting point and ending point is measurable with respect to the two slots. Okay, so in particular, for any pair xy, there exists a measurable path. Okay, this is jointly measurable in all the slots, so that the cost of this path is within, say, delta optimal with respect to H epsilon here. Okay. And now, once we have this measurable selection for any coupling where we do have the velocity bound, the expected value when I plugging in x and y as the starting and ending random variables for my gamma sub delta, the expected cost is within delta range of my expected value of H epsilon, so nearly optimal here. And then the rest is try to construct a measurable or admissible control for U2 epsilon from this gamma sub delta here. Okay, so I just copied what we have so far up here. So this is due to the measurable selection theorem, and I'm not going to prove it. All right, so next I have to use the randomization I promised before. So Cassie is an independent Gaussian. Okay, this is very good because it says I can recover any coupling just using Cassie. Okay, so in particular, when I fix the coupling, say x and y, there always exists broad measurable functions f sub x and f sub y, which are defined on RD, so that in the distributional sense, x is equal to f sub x of Cassie. Okay, similarly for y. So this is actually a randomization technique. So because we have the nice independent Gaussian random variable, we can recover in the distributional sense any coupling. And now we just take our path gamma sub delta and try to construct our control. So here I have alpha tilde sub delta, which is defined by the velocity of gamma sub delta, where for the third and second slot, I plugging in my two measurable function here, f sub x and f sub y here. So this control is indeed defined on RD. So the second slot I denote by Z, it comes in here and here. Okay, and then we define alpha delta, which is indeed the control lives in A2. I just plugging in Cassie for the second slot. So when I plugging in Cassie for the Z, right, so inside here, they becomes in the distributional sense X and Y. So this is the original path here I have. But this is indeed an admissible control in A2 because it's measurable with respect to Cassie. Okay, so let me clean things up here. So far, what we have is we can recover this coupling by Cassie, and we can show that gamma sub delta here gives us the admissible control for A2. Okay, and then we can try to verify the corresponding process by taking the integral of our control in the distribution. This is equal to indeed gamma sub delta. Okay. Okay, and then now we have this admissible control and the corresponding process. By definition of U2 epsilon, this is less than or equal to the cost for this particular choice of control and process. And then up here, by measurable selection theorem, we know the cost when I plugging in this particular path, it's nearly optimal, which means this is less than or equal to the expectation of this H epsilon with some small arrow here. And now I can take the inf on the right-hand side over all coupling x and y with this velocity bound. Then I can show U2 epsilon is actually less than or equal to U1 epsilon plus some little delta here. And then we let delta go to 0. Indeed, we have U2 epsilon is less than or equal to U1 epsilon. And then because we have the reverse inequality, so the inequality here are actually all equal. Okay, so U1, U2, and U epsilon, they are all equal. And also, more importantly, we have a formula in between here for U epsilon. So let me summarize here in the corollary. So the new formula we have here is U epsilon is equal to basically the expectation of my cost function H epsilon over the admissible couplings and the terminal measure here. And then the nice thing about this H epsilon is we already know a lot of information. So here I'm restating the theorem from Chen Yu where they proved as epsilon go to 0, the limit does exist. And we have a quantitative relation between the two. So in particular, the difference between the limit and H epsilon is O epsilon. Here, the constant would depend on the average velocity here. Okay. So now if we try to use this and then look at our U epsilon, we can redefine a new function U bar, just replace this H epsilon by the limit H bar. Okay, I call this value function U bar, which is the cost of this part over the same coupling and the terminal measures. And then we can compare this to H epsilon and H bar. So the theorem above and the velocity bound together actually implies the expected value of the difference of these two terms is bounded by some constant times epsilon. So here we do need the velocity bound. Okay, so in particular from there, we can get the O epsilon rate between U epsilon and U bar. And then later we still need to identify U bar with U, but this is already known because there is a relation between H bar and L bar. We can directly identify U bar is actually U in this case. And then this concludes the proof. Okay, so this is for the easier case. And then for the multi-scale case, we also have a similar result as in the finite dimensional case. So the rate actually depends on the time. So here the time big T minus C, this is the available time we have for the whole process. And when the time is larger than square root of epsilon, the rate is O square root of epsilon. And then when the time is relatively small, we have a little bit better O epsilon rate. Okay, I probably don't have time to go over the proof ideas here, but it's very similar to the finite dimensional case, but we have to be careful about the measurability in the proof. But the basic idea is we try to cut the curve, optimal curve into n pieces. For each smaller piece, we fix the cost at the beginning for the large scale variable and the measure together, where n is to be determined. And then when I fix, I have an error of 1 over n. And then when I do the homogenization for each piece, I have error of n epsilon. And then to choose the best n, which is basically 1 over square root of epsilon, we have the rate is O square root of epsilon. Okay. And then we also have application for dynamic optimal transport, where before, right, so the terminal measure can vary, can take any nu. Here we can fix nu and then define the cost function to be, the value function to be U epsilon sub OT with this fixed initial measure and ending measure. We have a similar homogenization result for the for this dynamic optimal transport problem, where the rate is also O square root of epsilon in the multi-scale case. And then, so here are some future work. We are still working on the first one. So here we are considering adding more complexity to the dynamics. So we want to add Brownian motion and see how things changes. And then my collaborator, he is interested in more complicated coupled systems. And maybe later we will do boundary condition problems. And then this is the end of my talk. Thank you very much for your attention.
Okay, thank you. Yuxi.
Thank you.
All right, so is there any question, comment from audience?
Yeah, actually, I have one question, please.
Yes.
Sure, go ahead.
Thank you for your very interesting talk. So my question is that I'm more familiar with the Hamilton-Jacobi equations in the usual case on the whole space RD or the torus D dimension. So this is the first time I see a Hamiltonian with an integral. So can you please explain me where is that integral come from? Thank you.
Okay. Sure. Let me go back there. Okay. So for this integral, yeah, so I would say if we want to rigorously derive the whole thing like this, we need to look at Ito's formula. Okay, so we have to go from Ito's formula and then derive. So let me think. So the most general case for this equation is second order. And then how they derive is they look at the dynamics, I mean the SDE, and then try to apply Ito's formula for the value function with increment, and then they try to prove the dynamical programming principle and try to derive this equation. So yeah, so that's why they have the integral there. Yeah, I don't know if this explanation makes sense.
Yeah, I think it's natural. Like your explanation is clear, right? And then also that the integral here with respect to m, right? You can think about m as the so C was talking about the population when you have the whole population, but you don't see each of the individual. You only see let's say you only see the density of the whole population, right? So this integration is integrating with respect to m, which is the density. It's natural in the sense that in a way you don't see individuals, but you only see the mean field with respect to m.
So this is a kind of setting for a mean field problem.
Yeah,
right?
this is, yes.
Thank you very much, Professor Hung and Professor Han.
Yeah.
Thank you. I'm not a professor yet.
Your title is a professor.
I have a quick question. So the quadratic rate requirement is because you stay to Hilbert setting.
Yes.
You assume it's p square.
Yes.
Is it easily generalizable if you go to I don't know, Banach space or something?
Yeah, so I think we try to do that, but it's not very easy because so the thing is here this quadratic growth is try to match the Wasserstein 2 distance. So everything can be lifted to the Hilbert space. If we don't know whether, so if we don't lift, right, so we can look at the equation and then, sorry, maybe I will just go here. So we can look at the equation and then try to define the solution to this equation in general, in the intrinsic sense. I think the well-postedness is not proved yet.
Mm.
Yeah, so it's still open. So that's why it's hard to do it in the intrinsic sense, in general.
Okay.
Hi, Yuxi. Thank you for a great talk.
Yeah.
And I
Thank
have
you.
a quick question, maybe.
Yeah.
So you mentioned that you guys are working on the more complicated case with SDE as your states, as your dynamics. If you have another randomness in your dynamics, maybe you cannot exchange the infimum between the pairs and the. Am I right?
Yes. Yeah. Yes.
In
Exactly.
that case, it seems so this way might not work. Am I right? Maybe you need some new method.
Yes. Yes. Yeah. Because in this example, we don't have Brownian motion, and then we proved the equivalence of all the controls, right? What it means is essentially, even though in the very beginning I'm not allowed to look into the future, right? So everything is progressive measurable, but I proved it's equivalent to just look into the future. That's why when I prove they are equivalent here, I have this H epsilon comes up, because this is a cost function which says, okay, you fix the starting position, and you fix the ending position. And then I try to minimize the cost. Okay. If I'm not allowed to look into the future, I cannot fix the future point, which means I cannot consider this function H epsilon directly. Yeah, does that make sense?
Yeah. I feel like because your randomness is mainly coming from your M, so it's like there's no future. I don't know. Anyway.
Yeah.
Thank you.
Yes.
Yeah.
Thank you for the
This much.
question.
This is very clear. Thank you.
Thank you. Yeah. So yeah. Well, yeah. Indeed, like there's no difference whether you look into future or not. But it was not clear for us in the very beginning. Because of this progressively measurable thing. Like the initial condition still can be random, right? So controls are still random. Yeah. So this is actually not obvious at the first. Yeah. But yeah.
Yes, of course. Thank you.
Yeah, but this is surprising. They are actually equivalent. Yeah. Thank you for your question.
Okay, so maybe let's close official question time, and let's stop record.